and hopefully you can get along. First of all, did anybody get 435? The coupling of the quark spins, do I need to do it?
Just about half enough.
Yeah, we're good.
Okay. Let me just go over it quickly because it all of a sudden went from the coupling of 2 angular momenta to the coupling of 3 angular momenta. So 435, let's do mesons first. In mesons, I always kind of remember medium weight, but it doesn't go by that because we found heavier and heavier quarks. But I always think medium is a 2-particle thing, and so it's a 2-quark meson. And same with baryons and everything. The leptons are supposedly light, but some of the leptons, you know, the 3rd generation leptons are incredibly heavy. So it doesn't really work, but it helps me remember things. So mesons are quark antiquark pairs. All right, and quarks have spin of a half. Each quark has spin of a half. It has spin 1 equals a half, and the other is S2 equals a half. All right, and so the idea is that we're going to couple together the spins of the quark, and so this is what I always do. We can draw the picture. We can go S1 plus S2, so the maximum equals 1, and then the minimum amount of angular momentum that this system can have is an S total equal to 0. And again, what I like to do is I like to draw a cloud around this, and the idea is the sum of the torques external equals I alpha equals dl dt. And if there are no external torques, what it means is L total must be conserved. So the question is okay, what is the L total of the system? And it's just a simple vector addition problem. If I have 2 angular momentum, they can add up, of each equal to a half. They can add up to 1, or they can add up to 0. All right, so for the other way to write this is you can just do it without drawing a picture, is you can say that S1 plus S2 is greater than or equal to S total, which is greater than or equal to S1 minus S2. All absolute values, so this is going to be a half plus a half is greater than or equal to S total, which is greater than or equal to a half minus a half, which means that S total can equal 1, and S total can equal 0. All right, so this is the total angular momenta, if we want, we can write this as S total, and then MS total. So now we're not just talking about that. Once we know what the total angular momentum is, then we can have the range of the possible projections of angular momentum. And for this state, we can have, if it's a 1, we can have a -1, 0, 1. So I get lazy and write the 3 states like this. All right, but that's literally 3 different states, 3 different projections of angular momentum. And so this is called the triplet. And then for this one, S total is a 0, and the only projection of angular momentum is 0, so this is called a singlet. Okay? So the other thing that this problem notes, that it said that assume that everything's in the ground state. All right. Now, why do you want to assume that everything's in the ground state when we're talking about the sum of angular momentum?
Because that's the lowest possible value it could have.
Okay. So what is the angular momentum of something in its ground state?
H bar over 2.
Okay, it's probably 0, you know, like an s orbital. All right, so we're talking about the quarks being in the ground state, having no orbital angular momentum. All right, and so later on we do the problem, it's 436, where we do an atom that has angular momentum. All right, and I want to make sure I do
The
that.
ground state got 0, so it would be the plus and or minus.
The whole thing is,
So this just means angular.
The lowest possible underneath.
so here's the scoop, guys.
But it still is.
Angular momentum, is it an angular momentum? Like orbital angular momentum, is that an angular momentum? What does it come in chunks of? H bar. Spin is intrinsic, right? It just is born with it, all right? But what are the units of it? It's an h bar, it's an angular momentum. So if I do have orbital angular momentum, and I draw my cloud around here and I say, oh, what are the possible values of angular momentum that I could have? I would have to include the possibility that I had orbital angular momentum as well. All right, but this problem says, forget it. We don't have any orbital angular momentum here. All right? We'll see as we go, all right? I think it will clear up a little bit more. But don't forget, angular momentum is angular momentum. It doesn't matter whether it's intrinsic or whether it's R cross P. All right? It's all, once you have angular momentum, whatever it is, it's treated the same. Okay, so the next thing in 435 is they say look at baryons. And baryons are 3 quarks. So quark 1, quark 2, and quark 3. So I'll draw a cloud around them, and it's the same game. If there are no external torques, if there's nothing acting on this system of quarks, what has to be true about the total angular momentum inside? No.
It's conserved.
It's conserved. Okay, so then the next question is, if it's conserved, what could it be? So then the only question is okay, if it's conserved, what could it be? Well, now it's just a practice of adding up angular momentum.
Maximum and minimum.
Okay, that's right.
If everything's a half, it's 1/2 plus 1/2 plus 1/2, which is 3
Yeah.
halves.
Exactly.
And then its minimum would be 2 of them cancel each other out, and then we get a half
Good.
left.
Here's how I do it. When life gets a little bit harder and you do something else, oh, before I go on, this question stipulates that these quarks are in the ground state. So what are we going to assume about orbital angular momentum? 0. So what is the only angular momentum we're talking about? Spin. Okay? So in other words, what we have here is an S1 equals S2 equals S3 equals a half. All right, so here's one way to do it, all right? So that you don't screw up, all right? And you can do it in your head and you'll probably get it right, but here's how I do it so I don't screw up. I go, S1 plus S2 is greater than or equal to S total 1, which is greater than or equal to S1 minus S2. All right, so we have a half is, we have 1 is greater than or equal to S total 1, which is greater than or equal to 0. So S total 1 can equal 1 or 0.
And then you have S total 2, which is a combination of those two plus a half minus a half.
So now I'll do the next one. So then I can do S total 1 plus S3 is greater than or equal to S total 2, which is greater than or equal to S total 1 minus S3. So this is going to be 3 halves is greater than or equal to S total 2, which is going to be greater than or equal to a half. All right, but then I have to also do S total 1 plus the second S total 1. I'm running out of subscripts here. S total 1 prime plus S3 is greater than or equal to S total 2 greater than or equal to S total 1 prime minus S3.
It's going to be 0 plus a half and 0 minus a half.
Right, so now over here, here's one thing that you should always do is take the absolute value of that. Right, because remember, what I'm saying is that I'm not concerned with its projection, I'm just concerned with its magnitude. All right, what is the total angular momentum that I can have? All right, so over here it's going to be a half is greater than or equal to S total 2, which is greater than or equal to a half, right?
Yeah. Which
Yeah.
half is equal to a half.
Yeah, so what we have, it could be different if the angular momentum is different, so that S total 2 can equal 3 halves or 1 half. And if I have a total angular momentum of 3 halves, how many projections can I have of 3 halves? Of a total angular momentum of 3 halves?
3 halves, 0,
No.
no, 1, 0.
So angular momentum comes in chunks of h bar. Even though fermions have a spin of a
So it'd be
half,
1, 0, minus
after that,
the half.
fields only have chunks of
So
it.
1, 0, negative 1.
So it's going to be no,
2, 3,
minus 3 halves, minus a half, 1 half, 3 halves. So go from 3 halves to minus 3 halves. Everybody, people are perplexed here. Jeremy?
Because
Oh, I get it, now it's a full.
they'll go up and down by 1, so it's. even though-
Yeah. So what I found here is, look, the total angular momentum that my system can have is 3 halves. So look, here's 3 halves. So yeah, I can have a 3 halves and I can have a 1 half. Okay? So the next question is, what are the projections that I can have?
It can be plus 3 halves.
And this would be a half, or if this were oriented downwards in some
Minus a
case, then
half.
this would be minus a half.
And have a 0.
So you go from 1 half to minus a half in steps of 1 chunk of.
We wouldn't have a 0 in there.
Right, and then over here, you're gonna have 3 halves, or you could have the 1 half. You
Negative
know,
1.
so this vector is out more like this, and then it's over like this.
1 half.
Yep. And then like this.
So negative 1 half, negative 3 half.
Minus a half, minus 3 halves. And like David said, neither one of these systems can you have a projection of orbital angular momentum equal to 0. Because if I have a chunk of 3 halves, and I go down by 1 chunk of orbital angular momentum, I can only end up at 1 half, and then go down another chunk, and it's minus a half. All right, so this one would have 4, and then this one would be a half, and how many would it have?
A half and a minus a
A
half.
half and a minus a half, and so this is called a doublet. So this is a doublet, and this is a quartet. All right, but it's quite general, all right? I'm doing things with spin, but we don't have to do spin. We could do it with angular momentum, and you can mix angular momentum, and you can mix spin, and things like that. And there's different strategies to do inside of that, okay? All right, so that's kind of cool. By the way, just real quick, I have the 3 halves. What are the spins of those quarks that they're all, if I'm in the 3 halves total state?
They're all,
We'll say I'm in the 3
Oh,
halves,
same
say
direction.
3 halves, 3 halves.
they're all in the same direction.
So they're all spin up, right? So isn't that a violation of the Pauli exclusion principle,
Yes.
right?
I have to pay.
So can I have this state?
You can't have 3 halves, or 3 halves, negative 3 halves.
Can I have that?
No. Well, if they're protons and neutrons, not if they're electrons.
Okay. So the answer is,
They have to be different, they'd have to be different things.
okay, so very good. So the question, this would equal an up, and up quark in its ground state. So I could do it an up with, so what I could do, it would be an up, let's write down, an up with a half, an up with a half, and then an up with a half and a half. What is the half, this first half?
That's the magnitude of the spin.
Just the magnitude of spin, and it's always going to be a half. It's a fermion, it has total spin of a half. What does the next half have to do with?
It has to do with its projection.
Okay, the projection. So then the question is,
If they're an X, Y, Z maybe?
okay, very good. So the answer is no, right? Unless quarks come in color. All right, and there's an additional degree of freedom. So what if, would this be okay? What if this was an up, red, up, blue, half up, green?
That would work, because then wouldn't have any color.
Okay, it would work because we don't have any color, but all of a sudden we buy our way out of the Pauli exclusion principle too. All right, and I think this is called the delta plus plus. All right, because let's think about this. This is an up, and up is 2/3, 2/3, 2/3. Right? Up, red, blue, green, up quarks. So what's the total charge on this thing? Of this baryon, it's a +2.
Two.
So I think this is called a delta plus plus. Right, just a little bit of extra stuff here. Okay? All right, problem 436. All of a sudden, what we start doing is we start introducing orbital angular momentum into the picture. And you shouldn't panic. All right, orbital angular momentum, same thing as spin. We actually get a different letter to use, so it helps us out a bit. So let's do this one.
And you have to learn how to read the chart.
Then I'm going to do Clebsch-Gordan coefficients, and I did find a Clebsch-Gordan coefficient calculator on the web. Did anybody find that?
Yes.
Which one did you use?
I didn't download, I just found it.
Yeah, but which one?
Oh, there's one that,
I just found it.
I
I was going to play around
used
with
it. Yeah, you the,
Was it the UK?
Yeah, I think it was from physics.
you had to actually figure out what the values of M could be using.
Okay, well, let's get there. Let's do 436 next, okay? So it says particle 1, so particle 1 has spin 1 and particle 2 spin 2. So look, now I'm just going to say, here's 1, it has s equals 1, and then here's 2 with s equals 2. All right, and they're at rest in a configuration such the total spin is 3 and z component is h bar. So, okay, so let's go through this approach first, all right? What are the again, we have this system. What's the possible angular momentum that this state could have? What's the total spin possible for this system?
3,
3, 2.
1.
Okay, so we would have 1 plus 2 is greater than s total, which is greater than 1 minus 2 absolute value, or 2 minus 1. So s total could equal 3, and s total could equal 1, right? So what are the possible values of s total? 3, 2, and 1. Okay? So what are the possible states that I could make out of this? And what I mean by that, the total possible states, the total possible spin states, will represent the total spin and the projection of the spin.
3 can be 3, 2, 1, 0,
So we could have
1,
3,
negative
2, 1, 0, minus 1, minus 2, minus 3. So there's 7 right there. And then the 2 will have
2, 2, 1, 0, negative 2.
Yeah.
And the 1 will have 1, 0, negative 1. So you got a triplet, quintet, and a septet.
Very good. I didn't know all those names. All right. Now, what they're asking for in particular is which state in this problem. Do you remember? So read the problem. Okay, so they're saying that in particular, that we're looking at a state with S total equal 3, and then a projection equal to H bar. So MS, right, MS equal to H bar, so what would MS be? 1. So what they're looking at out of all of these things is this particular one. So we're looking at a 3, 1. So let's write this as S total MS. Okay, and now we're going to get into the idea of the Clebsch-Gordan coefficients. All right? So this is what I would call my coupled state. Why is it coupled? Because I've coupled the angular momentum to form some total angular momentum. Right? Now, what I would call all of these things, I would call these my, these are all my coupled. All right? But what do I have here, for example?
Individual.
Yeah, so let me write this. This will actually work nicely, guys. Check it out. These are all my coupled states. The original thing I had, how about if I wrote it like this? I'm going to write it as a 1, right, because there's a total angular momentum of 1.
With a 1, 0, negative 1.
And it would have a minus 1, 0, 1.
So the bottom, out of the coupled states, the bottom 2 coupled states are also your individual states because you have a 1 and a 2.
I'm not sure I follow that. Let me follow this and see where it goes, okay?
Right.
All right, and then this is uncoupled, and what would this be? This would be a 2, minus 2, minus 1, 0, 1, 2.
Which, again, for particle 1, having a 1, it's the triplet. 2 is
I wouldn't go that far, David. I mean, they're not the same.
Well,
Because
that's the values, but
they look the same and they have the same name, but this truly represents the coupled state of the whole system, not just the one. All right?
a couple of the last two couple states have the same values as your uncoupled state.
Okay.
You know what I'm saying?
Yep. Okay. So now the question is, look, here's what I really have uncoupled. All right? And here's what I have coupled. So this, once again, is kind of like a Fourier series. Like a Fourier series, f of x equals some summation of the CNs on, you know, sine nkx. Yeah, we'll just use, that's a good basis set. The signs are linearly independent, all right? So, well, I usually write a plus b and cosine nkx.
And that's
Right.
your simple harmonic oscillator.
Yeah.
Which-
In any case, I've got a nice basis here. All right. What I want to do over here is I want to build a basis set for my original things. And so my claim is, look, I can build this as some combination of S1, MS1 times S2, MS2. Where if I were to give these a name, I would call these states S1, MS1, and this state would be S2, MS2. So maybe this isn't coming out so neat. All right, and again, the reason why I multiply these together is because these are linearly independent of each other. If you want to think of it, think of these as like separation of variables, you know, that we've been doing all along. And when you assume a separation of variables answer, you multiply the two things that you've separated together. And so these two uncoupled spins that we're beginning from are linearly independent, so we can build it like this. Oh, we need a coefficient right here, and we'll call this our Clebsch-Gordan coefficient, our CG. All right. So this is, you've got to understand that idea, how to start off. Okay? So here's what I'd like to do. Let's start to build it. All right, so here's some Clebsch-Gordan, and then it's going to be times this, and then let's put in 2 Clebsch-Gordan.
Well, depending on what the numbers multiply out to,
Yeah.
total ST could be, depends on how many
Of course.
you need.
Yep. All right, but what can I write in right away?
That's
Well,
S1 and S2.
That S1 and S2, because do those change? No, those are the things I'm building on. So I can write in S1, and S1 is a 1, and then which one is this going to be?
2.
And that's going to be a 2, and this is going to be a 1, and this is going to be a
2.
2. All right, so what I'm saying is, look, the only thing that changes in this new basis set is the projections, right? The total magnitude of the spin of the angular momentum, that doesn't change. It is what it is. Okay, so now I'm building the state of 3, 1. It's kind of a coincidence that 1 and 2 add up, but I mean, did it have to be that? Because could I have built this state and would it have looked the same? Yeah.
It's just that the fact that the books.
The book just asked for this one.
All
All right, so hell, the book did 3, 1, I'm going to do 2, 1.
Alright.
All right? So does it bother you that 1 plus 2 is 3 and that's not 2?
No, because it's somewhere between the maximum and minimum.
That's right.
It's actually
That's right.
vector addition.
That's right. It doesn't matter. It's vector addition. All right, and so this is going to be a 1 and a 2 as well. But what about this number?
That you gotta add that MS1 and MS2
that they do have to add up because that's what it's saying out gut for a total spin. All right, one way to look at this is that's kind of like the projection, it's a scalar. Once it's a projection, I guess it's a scalar. Yeah, it's the projection, right? As opposed to this represents the vector. Okay, so what Clebsch-Gordan coefficients am I going to need? Well, now I got to kind of look at all the different things that add up to 1. All right. So what have I got here?
For 1, you could have a 1, a 0, or a negative 1.
Yeah, there's going to be a lot, right?
For the 2, you could, if it's 1, 0, then it's 2, 1.
So let's start here. So I've got to start from the coupled thing, the uncoupled thing. So let's go 1 minus 1. Can I get to a 1?
You have to need a 2, 2.
You need a 2, right? So this could be a minus 1, 2, and then minus 1 plus 2, that equals 1. Then I could go a 1, and then I would need a 2, right? And then what do I got to do?
If it's 1, 1, you need 2, 0.
Yeah, so I screwed up later.
You need a minus 2.
So if I go 0, sorry, 0 is going to be a 2. Do I need another term? Yeah, I need another term. I need a plus Clebsch-Gordan, and then again I'm going to go do. Just put it right
Wouldn't
in.
it be 2,
So,
1?
so what do I
If
need?
it's 1, 0, wouldn't it be 2, 1? So you're trying to get a 1?
Oh, yeah, yeah, yeah.
Oh, yeah.
I'm jumping ahead, thank you. But you guys are right on the money. All right, and then I could go right here. I would need a
0, 1,
1, 0. All right, and I think that's it, right?
Yeah. Because the 1 can only have those 3 possibilities, so it'll make the 2 only have 3 possibilities.
By the way, guys, if you don't practice this, I find this one of the truly most confusing subjects to do. If you haven't come in here today wrapping your head out, then it's meaningless to even. You've got to have to bang your head for quite a while.
Ask Dale how to read the Clebsch-Gordan.
Oh yeah, it's
chart.
brutal. It's brutal. All right. So now let's go read the chart. All right. So what's the first thing I'm going to do when I look up on the chart?
I'm looking for a 1 by 2.
Okay. I'm going to
2.
look for. This chart has that I'm coupling 2 angular momenta. All right. The primary thing I'm going to look for is I'm going to be coupling together an angular momentum of a 1 and a 2. All right. So what I've got to look for is the chart that says, hey, I'm coupling together 2 angular momenta. 1 is a 1 and 1 is a 2. All right. So if I look at that chart, like Dave says, but it's a 2 times a 1, but it doesn't matter. You just got to keep trying to do this. So I look on the 2 by 1, all right, and then I look for what I want to build, and it's a 2 by 1.
You gotta look for the column that says 2 by 1.
Yep, so I'm looking for it.
That's in the second, the first big bracket.
So 2 by 1, yeah, I see it, my eyes are failing me. All right, and then I have 3 Clebsch-Gordan coefficients,
right underneath that.
all right, and so the first one is a third. And then what I do is I follow the third all the way to the left. And when you follow it to the left,
It gives you,
it's the 2 and a minus 1. So that means it goes to the 2 and the minus 1 thing. And that one becomes 1 square root of the third. So this becomes 1 over the square root of 3. Or all that. Okay, then I go down and it's a 1/6. And that has to do with the 1, 0. So the 1/6, the 1, 0, that's this one, right?
yep, the second one.
Well,
No,
yeah.
the last one is.
Yeah, you got to remember which one. They went the opposite
No,
way.
2, 1, 1, 0.
Yeah, it's the middle one.
It's the middle one?
Middle one, because that was 2, 1, 1, 0.
Okay, and that's going to be 1 over the square root of 6. So the square root of 1 over 6. And then the next one is
Minus a half.
minus a half. So what does the minus mean?
Minus the
Negative.
term.
It's a negative Clebsch-Gordan coefficient, so it's a minus. And then what is the
1 over the square root of 2.